Hi everyone, I'm Aman, and today I'm going to talk about our work, Think About It, Improving Defeasible Reasoning by First Modeling the Question Scenario. This is a joint work done with Niket, Dheeraj, Peter, Iming, and Ed. We know you have a lot of papers to CAT, and LP, so I'll start with a short pitch. Our setup is as follows. We are given a question which is fed to a graph generator to generate a graph that models the question scenario. Both the graph and the question are fed to a hierarchical mixture of experts model to generate the answer. In the following slides, we'll try to ask and answer the following questions. How can machine-generated context be used for better reasoning? How can we go beyond GCNs for learning graph representations? And how can we do explainable and effective reasoning over graphs? So with that, let's begin. This is the outline of this presentation. We have two different parts. In the first part, I'll introduce the feasible reasoning task and discuss how graphs can be helpful for defeasible reasoning. In the second part, I'll introduce our model for question answering. So let's begin by introducing defeasible reasoning using an example. So we have a premise, a contagious virus is spreading. Based on this premise, we have a hypothesis that Rob catches the virus. And suppose now we have some new update. Rob does not wear a mask. The question is based on this new update, does this update strengthen or weaken the hypothesis? In this case, the update strengthens the hypothesis. So formally, the task is as follows. We are given a premise, a hypothesis, and an update, and we want to find out if the update increases the probability of the hypothesis as opposed to when we were given just the premise. We have a large data set for this task. Thanks to Rachel and team, they introduced a defeasible reasoning data set over three different domains, common sense, social norms, and NLI. And the data set is fairly large, spanning 40,000 to 90,000 rows for different domains. So now let's see where do graphs come in the picture. So let's go back to our example. A contagious virus is spreading. We had the update, Rob does not wear a mask. We had the hypothesis that Rob catches virus. In this case, the update strengthens the hypothesis, but usually that happens via a mechanism. So the update causes more virus to enter the body, and which in turn increases the probability of the hypothesis. Similarly, there could be some contextualizers, some contextualizing situations, external situations that cause the update. And similarly, we can think of a different update, lower infection rates, and again, they might weaken the hypothesis. So lower infection rates decrease the odds of getting in contact with someone with the virus, which in turn decrease the odds of the hypothesis. And again, there could be external situations. So a graph sort of fills more information of different kinds around the query, mediating information or the contextualizers. The use of graphs for defeasible reasoning has been noted earlier, notably by John Pollock in this work, where they propose argumentation graphs for defeasible reasoning which capture very similar information. In a prior work, we have produced a corpus of such graphs. So we have pairs of defeasible queries and machine-generated graphs that are grounded in the query. So concretely, we have a parallel corpus of defeasible query and graph pairs. And the graphs are grounded in the query, as you can see. In that work, we also found that these graphs help humans at defeasible reasoning. So performance of humans goes up for all three domains, sometimes by a large margin. But humans used graphs in a very interesting way. So they used different parts of the graphs to different degrees. And it was not the case that graphs are always helpful for them. So they would pick and choose. So they would first pick parts in the graph to see what's useful, and then sometimes they would discard the graph altogether. This motivates our method, which I'll talk about next. So we have a query, we have a graph, and we want to see how can we best make use of this graph to answer this question. Let's talk of some simple baselines. Of course, the first baseline is that we will not use the graph at all. We'll just use the original query. The second baseline is that we'll append the graph as a string right after the query and fine tune. In both the cases and for the rest of the experiments, we use Roberta as our encoder. So we see that this simple baseline of appending the graph as string already helps across the domains. So there's some useful information in the graphs, but can we do better? And we think that the string baseline might not be optimal because it does not really highlight different parts of the graphs. It's just a flat string. So we have to rely on the model to kind of figure out that different parts of the graphs have different semantics or maybe noisy and so on. And we find in the human evaluation that when humans use these graphs, they didn't use all of the graph, and sometimes they actually discarded the graphs. So we want a model that can act in a similar way. So the model that can selectively use parts of the input and then can sometimes discard the graph when it has too much noise. So for graph-based QA, we experiment with one more baseline, which is GCN plus attention, and then we show our model, which is hierarchical MOE. So the GCN plus attention model is derived from LV et al., noted here. Briefly, we have a query, which is encoded as HX. Then each node of the graph is encoded using the same encoder, and then we run GCN over the nodes. The encoded query is used as the key to run attention over the nodes of the graph after they've been through GCN to pool the node representations into a graph representation. And both the query and the graph representations are added and sent to the classifier. Well, this is good, but the graphs are machine generated and GCNs propagate information, but in this case, they could be propagating a lot of noise. And recall, we want to pick and choose, which is not happening here. So to remedy this, we use MOE, mixture of experts. It's a module X is the input, Y is the output. So let's see what's going on in here. The first step is that the input is transformed by n different experts, E1, E2 through En. So the input goes in, each of the experts takes the input and transforms it. Then the input is also fed to a gating network, the same input, and the gating network gives out weights with which we combine the output. So the output is essentially a linear combination of the inputs weighted by the p-values. The training happens end to end, and the hope is that each expert learns to separate the input into a meaningful view, and then M, the gating network, acts as a manager and can select the right expert for the job. We use two different MOEs. So we encode the query as before, we encode the nodes as before. Instead of running a GCN, we run an MOE that kind of selectively picks and chooses over the nodes and creates a graph representation. And then we have a second MOE that blends the graph representation and the query representation using another MOE, which is finally fed to the classifier. So these are the results. As we can see, the MOE model outperforms both the string and the GCN baselines. The GCN baseline actually performs slightly worse than the string baseline in a couple of domains. And again, we think it's because of the amplification of noise. And what are the MOEs learning? So the first MOE, which is the MOE over nodes, we can now tell because we can look at the gate values. So we see that for different domains, the different parts of the graphs, there's a very different way of using. So for atomic, all the three parts of the graphs are used to the same degree. For social, the situation is used the most, and we think it's because the social domain has no context. So the graph which supplies an external context, the model uses it to answer the question. Similarly, we find that for the second MOE, when the true label is strengthens, the graph is used more, and that sort of indicates that graph has more reinforcing evidence for cases when the right answer is strengthened. And finally, the heat map shows the correlation between different parts of the graphs being chosen. And what it shows is that correlation across different parts of the graphs is either negative or very small. So for instance, it's not the case that both contextualizers and mediators are used at the same time. So it indicates the graph uses that the model uses one of these components depending on the question. So in summary, thinking about a question scenario before modeling helps in answering the question, and the mixture of expert allows explainable and effective reasoning over the graphs. All the code, pre-trained models, data, etc. is available at this GitHub URL. Thanks for watching the video.